We are discussing the quality factor Q. So Q can be written as, if you have an inductive element, so it is omega R into L by R, right? If it is a capacitive element, so it is 1 by omega R into CR, right? So let us assume that, so we'll calculate, we have a resonant circuit. Okay, in case of RLC circuit, if you have an RLC circuit is there. Okay, so in case of RLC circuit, if the circuit is something like this, okay, so what is the maximum energy stored in this inductor? What is the maximum energy that's stored in inductor?
Of L I maximum square.
Of L I maximum square, right? So at the same time, so what is the energy stored in capacitor?
C
Half
VM
VM square.
VM square.
No, you just listen the question. If the inductor is having the energy which is equal to of LIM square, at the same time, what is the energy across the
Zero.
capacitor? Zero, right?
Zero.
Similarly, if this is 0, so it will be of CVM square. At any time, right, of LM square at resonance equal to of CVM square. So that means the maximum energy in the circuit, right? The maximum energy in the circuit is same. So it is transferring from inductor to capacitor, vice versa. If the inductor energy is maximum, capacitor energy is 0, and vice versa, right? So if you have quality factor, Q factor at resonance, Q factor at resonance. So you have QR, so that is denoted with QR, resonance. So it will be omega R LR, so which is equal to 1 by omega R RC. So everything is remain same. So only thing is that, so here the frequency omega now will become omega R. So here omega is becoming omega R. So if we have this omega R, so which is equal to 1 by square root LC, 1 by square root LC. So now you have QR, so which is equal to omega R L by R. Agree? So how to write this one? So you have omega R, right? So what is omega R? So this omega R can be square, it will be square root LC, right? Into L by R. So how to write this one?
1 by R into root under
1 by
L by
R
C.
square root
L by
LC.
C.
So this is another expression for resonant frequency. So this is the another expression for resonant frequency. So this is most commonly used, these two. So either you can express like this, or so this you can express this QR. This is the resonance Q factor at resonance. So this is Q factor at resonance, QR. So let us assume that, so this is voltage VL and this is voltage VC. So now we'll calculate VL. So what is VL if this current is I? What is VL if this is XL and this is XC? So what is V? What is VL? Voltage across inductor. How much it is?
I into XL.
I into XL.
I into XL, right? Okay. So this can be written as I into omega
Omega.
R into L, right? Agree?
Yes, sir.
Okay. So this can be written as, what is I? I is V by R, right? Into omega R L. So why it is V by R? So because it is at resonance. So this you rewrite this one omega R L by R into V. What is omega R L by R?
Quality factor.
QR.
Quality factor, right? So that is QR into V. What do you understand from this?
Quality
What?
factor is ratio of inductive voltage to total voltage.
For example, this voltage is 200 volts. Okay. If quality factor QR at resonance is 10, so what is the voltage across inductor?
20 volt.
So 2000 volt.
2000 volts, right? Okay. So the voltage across inductor is amplifying. So how many times or how much time it is amplifying? This QR times. Similarly, we see voltage across capacitor. So what is voltage across capacitor? I into XC, right? Agree? So what is
Yes, sir.
XC? I by omega R into C into I, right? What is I? V by R into omega R RC, right? What is V by R? V by what is omega R RC?
So 1 upon QR.
Why are 1 upon QR?
Directly QR.
V upon omega. No, no. So this it is 1
V
by
by
omega
QR.
R RC into V. What is 1 by omega R RC? What is
QR.
1 by omega R RC? So this is QR, right? So it is QR into V. So what you understand here?
So same thing only, so it's getting amplified.
So even though, right, even though the voltage is 200, even though the voltage is 200, right? So here the thing is that the voltage across the inductor and the voltage across the capacitors are magnifying. So how much times they are magnifying? How much times they are magnifying?
So QR
QR times.
QR times.
QR times they are magnifying. Okay. So now tell me, so this is an advantage thing or a disadvantage thing?
Advantage.
advantage, sir.
Why advantage? So here these capacitors are coming with some ratings. Okay. So these capacitors are coming with some ratings. We have some capacitor 400 volts capacitor. Maybe you can write 1000 microfarad or something like this. Okay. So this capacitor is having some rating. So these capacitors are designed to withstand some voltage rating. Similarly for inductor, so this is also designed to withstand some current rating, maybe 10 amperes, 20 millihenry, something like this. So that means this inductor, right, can withstand or can carry a current which is equal to 10 amperes and its inductance value is 20 millihenry. Okay. If you want 20 amperes, right, if you want 20 amperes inductor, so in that case you need to increase the dimension of the winding. Okay, you need to increase the dimension of winding. Simple thing. If the winding is right, if it is a thin winding, so it will carry less current. If it is a thick winding, it will carry more current. Right. So whenever inductor is there, whenever you have wound some wire, so that is having some thickness. So based on the thickness, we have current rating. Right. Similarly for capacitors, so we have voltage rating for the capacitors. So here for every one or every inductor capacitor is coming with some voltage rating in case of capacitor and current rating in case of inductor. Right. For example, this capacitor is connected here. So 200 volts is supplied voltage. If it is not in resonance, if the circuit is not in resonance, right, it will you can safely operate this one, right? We can safely operate this one. For somehow, some reason, if there is some resonance, right? If there is some resonance, either we have changed the inductance or we have changed the frequency. So what will happen if the QR is 10? So the voltage across this one is 2000 volts. So now what will happen to this capacitor?
Overload, sir.
So it's supposed to withstand for 400 volts, but you are applying a voltage or the voltage across that capacitor, so which is having very much high. So that means this capacitor will be damaged. So this capacitor will be damaged. Right? So here, right, So this capacitor will be damaged. Okay. This is our power electrical engineering point of view, okay, where we are handling the voltages. So whereas 230 volts, we are handling high voltages, right? 230 volts, 415 volts, something like this. We have other concepts also. So we have communication engineers are there. We have different branches are there. ECE, right? So in case of ECE, so they are handling very less voltage. So let us assume that this voltage is 5 volts. Okay, this voltage is 5 volts. So in this case, if you have still you have QR equal to 10, so what is the value of this capacitor here? At resonance, what is its voltage? So 50 volts. Okay, 50 volts. So that means this is, so why these resonant circuits are used? Because in resonant circuits, the impedance of the circuit is minimum. If the impedance is minimum, so we can pass the maximum current. If the current, this current is maximum, in that case the signal strength will be maximum. The signal strength will be maximum. So that's why in communication circuits, so they are always at the resonance point. So the signal strength will be maximum, right? In case of communication circuits, so they always try to operate the circuit at resonance or near resonance or as close as possible to the resonance, right? But whereas in electrical circuits, we'll try to avoid the resonance. Understood? So why we try to avoid the resonance? If you have resonance in the circuit, so the current will be maximum, the voltage across the inductor or the voltage across the capacitor will be very much high. So therefore we will try to avoid the resonance. If it is not possible, so or we will try to restrict the quality factor, or we'll try to restrict the voltage across the capacitor or inductor. So here thing is that in case of electrical engineering point of view, right, the series resonance or the resonance phenomena is having negative effects. In case of ECE, so that is having the positive things. Understood? Because of the power handling or the voltage levels are high in case of electrical. In case of ECE, the voltage handling is very less. However, in electrical also, so with this resonance, we have some other, by using some other techniques or some other concepts. So there are some, we can make this disadvantage into advantages, and we have some other applications also, so that you will discuss in, that you will learn in the later point of your courses, right? The brief thing is that, so in case of ECE, so there are a communication point of view, they'll try to operate as close as possible to the resonant frequency. But in electrical point of view, so we'll try to avoid the resonance, right? So you cannot completely say that, so resonance is a negative thing in the electrical, but we have some applications where this negative thing can be changed into a positive one. Okay? So that we will discuss, or we have some power filters are there, right? That is power filters are there. So those things, so those are working on the phenomena of resonance. In case of similarly, if you have induction heatings are there, right? So we have induction heaters are there, right? If you remember that, we have wireless chargers are there. If you remember this, wireless chargers. Okay. So those things are working in the principle of resonance. So that is, so how this negative thing is changed to a positive one. So that that is the different aspect. Understood? So what you have to understand that when the circuit in the resonance, the voltage across an inductor or the current voltage across the inductor and the voltage across the capacitor is amplified by QR times, is amplified by QR times. Okay. You have any questions? So that's why it is known as voltage multiplication factor. So that's why it is known as circuit magnification factor. So that's why this Q known as this quality factor is also known as circuit magnification factor. Okay. So from this also you can derive the QR. QR can be written as, so QR can be addressed as either VL, QR can be, so this QR so can be written as, in terms of VL and VR, it may be VL by V or VC by V. So this Q is known as circuit magnification factor, circuit magnification factor. So generally, right, in general, so there is no rule here. So in general, in case of ECE circuits, this Q is usually greater than 10, right? But in case of electrical circuits, so this Q value may be somewhere between less than 5, or you can somewhere less than 5 in case of electrical circuits. If you remember, if you are aware that you have fans are there, right? You can see that, so will be a capacitor. So there will be a capacitor. If you see, if you open that in the fans, so there will be some small capacitor will be there. Okay. So why that capacitor is connected are, so fans, induction machines especially, or fans, right? If you have a microwave oven or not microwave, if you have a what we say, if you have equipment like washing machines, air conditioners, and maybe what we say, vacuum cleaners, right? So most of these things are equipped with single phase induction motors. Even if you have a pump sets, right, for extracting the underground water, so you may have pump set, right, motors. Okay, we have well motors are there, we have some semi-merged motors will be there, right? So those things have induction motors. So the thing is that three-phase induction motors are self-start. That means, so no starting mechanism is required for three-phase. But in case of single phase, so these are not self-start. So why it is not self-start, you're going to discuss in your later point of classes, right? So these are not self-started. To start this one, so we usually connect capacitor across the circuit, or across the motor. So we usually connect a capacitor, right? So these capacitors, so at starting, so they will be at resonance with the, so this induction motor is having some inductance. So that means the circuit may be in the resonance with this induction motor. So that's why you usually take, so the Q quality factor usually 1.5 times the quality factor. Okay, so here 230 volts supply voltage. So this voltage across this capacitor may be 1.3 times. So this much of times. So it is usually roughly operated at a quality factor, which is equal to 1.5 times. So this is the application of resonance. So it is used to boost the voltage across the circuit so that it may be, right, it may be helps in starting of the motor or developing the torque in the motor. So if it's self-starting means, so the torque, so because of the torque we have rotations, right? So that means it is not producing any torque. Okay, you'll learn these things in just once you learn these things, you are aware of these things, right? Okay. In case of communication circuits, so usually sometimes you have Q value which is equal to 300 also you can find. Understood? Understood. You have any questions?
No, sir.
Okay, right. So next we have bandwidth. So usually this bandwidth is a general term, right? So we have bandwidth in communication circuits are there. So you have bandwidth internet circuits are there. What is bandwidth in internet circuits? You might
Free.
have heard, right? What is the bandwidth? The 100 Mbps, something like this. You might have heard this, right? 100 Mbps, 330 Mbps. If you have LAN connection, or if you have a router at your home, they're providing with certain bandwidths, right? Okay. Similarly, in communication circuits also, so we have bandwidth. Okay. So here in communication circuits, right, we have signal. For example, some signal is there, right? So the signal is, for example, if you have FM is there. So what is the frequency of this FM? What is the range
In
of this
terms of
FM?
kilohertz, sir.
Mhm.
Around 3000
Mega,
kilohertz. Or something.
megahertz,
No, if you have some channels are there, no, in FM.
93 point.
mega 92.3 or something.
So what is the range of the channels?
Megahertz, sir.
Megahertz.
What is that? How much you have heard
88 to
something?
108.
Sir, AM in terms of
108.
kilohertz and FM in terms of megahertz. Sir.
Mhm. So we have some frequencies is there, right? What is that range of that frequencies?
88 to 108 megahertz.
Yes, 88 to 108 megahertz. Okay. So what is the band here? So 20 or something, right? 20 megahertz. Okay. So here, so let us assume that, so this is 88 to 108 megahertz. Some signal is there. Right. So you have some receiver is there. Somewhere you have some receiver is there. So it's supposed to accept. So this is your FM radio. Right. It's supposed to accept this range of signals only, right?
स्क्रीनशॉट ले लिया भूत में फ्री लिया हाँ
It's
Sir.
supposed to accept or this supposed to receive. So this range of signals only. Agree? So that means if the signal is less than 88 megahertz or if the signal is greater than 108 megahertz, it's supposed to stop. Right. So these are known as, right. So here that means it's supposed to allow, so these frequencies. So these are known as, usually known as filters. So these are known as filters. Please turn off your mic. Ankit Kumar, Amit Kumar, turn off your mic. Right. So these are supposed known as filters. So we have different types of filters are there. So low pass filters, high pass filters, band pass filters, band stop filters, and notch filters. So low pass filters, so usually, so these filters, so will allow low pass. So low frequency, so whatever the filters, usually filters are tuned to some frequency. So below that frequency only, it will pass. So high pass filters, so between, so above the frequency, so that only, right, so that only it will pass. Band pass filters, so we have some frequency F1, F2 frequency is there. So in between F1, F2 only, so it will pass. So here what kind of filter is required? So usually band pass filter is required. So here it is 88 megahertz or 108 megahertz. Between that only it will pass. Band stop, right? So in F1, F2 band, so we have band like this, right? You have F1 there, F2 is there. So this will pass and this will pass. So this won't pass. Okay. So that is known as band stop. So we have notch filters are there. So these notch filters usually pass the specific frequency. For example, you have 100 megahertz frequency is there, right? So that means it will pass only that 100 megahertz frequency, right? So these are different filters are there. So these filters are associated with this bandwidth. Okay. So these filters are associated with bandwidth. So that means what is the bandwidth of the filter? So how much frequencies or what range of frequencies? So that is allowing. So that is known as bandwidth. Understood? So you'll learn more about maybe in your ECU circuits, maybe in your analog electronic circuits or somewhere. So you'll learn these things. So we have different filters are there. So this is in connection with this bandwidth. Okay. Right. So now we'll discuss. So what is this bandwidth in terms of resonance? You have any questions? Right. So come to our actual discussion. We have bandwidth. So let us assume that we have a resonant circuit. So what is the current, actual current in a normal circuit? If you have LCR circuit, something like this, you have some circuit like this. So what is its current? It's V by square root R square plus omega L minus omega minus 1 by omega C square, right? So how this current look like? How this current look like? We already drawn this, right? So how it look like?
What is an x-axis, sir?
So what is the frequency? Oh, sorry. What is the it is frequency, and this is I. So how it look like?
Sir, above frequency axis is the straight
So
line.
it start from
Straight line.
0, right?
Yes, sir.
It will be something like this, right? Agree? Agree?
Yes, sir. Correct.
So this one is, what is
At
your
resonance.
resonant current IR, right?
Yes, sir.
Your resonant current IR. So this one is, what is this? So resonant frequency
Resonant
FR.
frequency.
So this is 0, right? At infinite time, so the current reaches the 0 value. Okay. So what is the power at resonance? So this is the peak power, right? So what is peak power? What is the peak power in this circuit? What is this power? So this is equal to IR square into R, right? Agree?
Sir.
Okay. So here, what is off peak power? So off peak power, so there is I square R by 2. So this can be written as IR by 2, so IR by, not 2, IR by square root 2 square into R. Okay. Understood? So this is known as off peak power. So at off peak power, so what is the current value?
Sir, RMS.
What is the current value? IR by root 2, right? So it is roughly IR by root 2. So that means the current is 0.77. So here somewhere you have, so this one, so this is 0. In other words, I will try the actuals. So it is IR by root 2. Right? So here, so corresponding to this, so you have one frequency corresponding to this. So you have another frequency. So this is known as F1 and this is known as F2. So this F1 and F2, right? So this F1 and F2 are corresponding to the off power points of power points. Right. So the difference between, right? So the difference between F2 minus F1, so F2 is higher side, right? So this is known as bandwidth. The difference between F2 minus F1, so it is known as bandwidth. So this F1 is known as lower off power frequency, lower off power frequency, and this F2 is known as upper off power frequency. Understood? Understood? So here, so these are known as off-power frequency, right? So here, the difference between this F2 and F1, so this is the one, so this is known as bandwidth. So that is F2 minus F1 in hertz.
Sir, why we should take only half bit, sir? We
So
can
that is the
take-
definition. Okay. Right. So that is the definition. So this is the thing that, so they feel that, so this is the appropriate one. Okay. So between these things only, so here that is acceptable.
Acceptable means
That is by definition, right? So that means we have some curve will be there, right? So why it is exactly that, why we have limited that, so there is a reason for that, right? Okay. So if you know that, so in next step you may understand, right? So here, so what is the current I at that point? What is the current I?
IR by root.
IR by root 2, right? Okay.
Yes, sir.
So we have impedance Z, so which is equal to V by I, right? V by I. So it is V by, so what is I value here? So I by root 2, agree? Agree?
Sir.
So it will be root 2 times V by I. So what is V by I? What is V by I?
Impedance.
So that is V by I is
Values.
R, right? So root 2 times R. So Z is root 2 times R. So when this happen? So when it will be happen in this circuit? So you have Z, this is equal to, so Z is supposed to equal to square root R square plus omega L minus omega C square. So which is equal to root 2 R. So this is at frequency, this frequency and this frequency. So what it implies?
XL minus XC whole square
Omega L minus omega
minus
C,
omega
so which is equal
equal
to
to
R.
R.
Okay. So now the question is, so why we are exactly taking this? So the thing is that, so resonance is a phenomena. So when the frequency changes, so this point is changes, right? Okay. For example, you have some values is there. For example, you have 10 millihenry is there and 1000 microfarad is there. Okay. And this resistance, we have some values there, right? So every time this resistance changes or this values of, there is a slight change in this component, and there is some slight variations in this component or some slight variation in this voltage, right? So this resonant frequency will change. Agree? The resonant frequency will change, right? If the resonant frequency will change, so it is supposed to give the maximum current, but at that point it is not giving the maximum current. So every time theoretically, so we can obtain the maximum current or resonant point, but practically it is difficult to obtain the resonant point, right? So that's why we have some range of values. So that's why we have some range of values. Why exactly it is not obtaining? For example, you purchased a 1000 microfarad capacitor. So in the manufacturer itself gives you some tolerances, right? So what is the tolerances? Maybe 10, plus or minus 10% of tolerance or plus or minus 5% tolerance they will give. Okay, so that is one thing. And if the age is coming, right, if you are installed 1 year ago, see it may not be at 1000 microfarad. Either its value may be reduced or its value may be increased, right? So every time, so you cannot exactly tune our or tune the circuit at resonant frequency. So that's why we have some acceptable limit. So we have some acceptable range. So this is the range. So where that range is omega L minus 1 by omega C equal to R. So this is the acceptable range. Okay. So instead of operating exactly the circuit at here, okay, instead of operating the circuit at here, so they are operating with some ranges between these two, this range to this range. They're trying to operate. So that is the thing. Okay. So why we are not exactly operating at this point? Because of the variation in the components or variation in the load circuits, or due to the aging, the variation in the components, right? So those things are causing you to not operate at certain point. So that's why we have some relaxations are there. So what is that relaxation is? So that omega L minus omega C equal to, okay. So this circuit is in resonance only. Clear?
Sir, could you explain it again, sir? The reasoning for why we prefer IR by root 2 instead of IR?
No, we are not referring. See here, the thing is that every time, because these things are in megahertz, right? Okay. If there is a slight change in the frequency, so there will be change in the this current, right? Okay. So every time you cannot precisely operate the circuit at resonance. That is not possible. So why it is not possible? So maybe the load varies. Okay, if the load changes, the resonant frequency may change. If there is a variation in this inductor, so there is a change in the circuit. If there is a variation in the frequency, so then also the circuit may not operate the resonant point, right? Okay, so that's why they have taken some tolerances, or they have taken some limits. Okay, so instead of operating exactly here, so that means instead of getting a high, instead of getting a peak current, so they are satisfying with, so these currents maybe 0 or 1/3, or what we say, instead of getting a maximum power, so maybe they are satisfying, okay, off maximum power is okay for us, like that. So they're convincing. So that's why, so this concept is derived. Understood?
Yes, sir.
So sending information
So this
only
is
within
just
the
for
range of frequency.
yes.
Sending information only within range of these frequencies.
Within that range only. Okay.
Okay.
So here the thing is that the why we are at resonance means we want to send a peak power, right? Okay. So that is the main motto in communication circuits. We want to send the maximum power. So that means we want to send the maximum strength of the signal. So that is not possible every time. So that's why we have some acceptable limits. So instead of sending that, so they may accept for half of the peak power. So that is their range. So this is F2 minus F1. So that is known as bandwidth. So there is other definition of this bandwidth, right? Are also known as what we say in communication circuits. So we are defined a, so let us assume that this power is P1 and this power is P2, right? So this off power frequencies can be represented in decibels. So can be represented in decibels, right? So this can be represented as x equal to, so 10 log P2 by P1. So what is P2 by P1? So what is P2? So 10 log, so P2 is IR square R by 2 by IR square R, right? So what is this value? 10 log 1 by 2. What is log 1 by 2? What is log 1 by 2?
Minus
Minus
0.3.
0.
three.
Minus?
Minus 0.3.
minus point
So what is this
3 0
overall value?
Minus 3.
3.0
Minus
2 minus.
Minus 3 dB. Agree? Okay. Right. So these points also, so there is another one in communication circuits. So this F1 and F2, so these are known as minus 3 dB points.
Sir, that log, sir,
Yes?
that log is for base 10, no, sir.
I have written log, no? So that is for base 10 only. If it is ln, so that is base
Yes,
e.
sir. Yes, sir.
That is the one, I think. I remember.
Yes,
So
sir.
generally we represent ln. So that is for base e. If it is lg or log, so that is for base 10 only, unless is specified. That is correct only, right? You can also use
Yes,
lg, I
sir. Yes,
think.
sir.
lg or ln. lg or L natural logarithm or only log. Okay.
So what is this x, sir?
Mhm.
What does it signify?
What?
X. What is x, sir? What does it
So
signify?
this is 3 dB. So this answer is minus 3 dB points. Okay. So here x I assume something, right? So that thing is that minus 3 dB points. So here the frequency usually measured sometimes in logarithmic scale. So we measure the frequencies, right? Okay. So that is minus 3 dB points. So these things are known as minus 3 dB points. So this is just I'm saying in ECE point of view. Okay, and sometimes what will happen if you're going for some competitive exam, right? So there's sometimes they use the word minus 3 dB point. So meaning is minus 3 dB point means off power frequency point only. So that means he's talking about F1 or F2 only, right? Okay, so where we are, okay, yeah. So this is about F1 and F2. Understood, right? So now at F1, right? At F1, so what is the state of the circuit? We will draw again here. Right. So at the same time, so what is the impedance curve? What is the impedance curve? You
Straight
remember
line.
this, right? So what is the impedance curve?
Reverse of this, sir. Reverse of it.
It will be
Downward.
something like this, right? Agree?
Yes, sir.
So what is this value? So this is corresponding to FR, right? So what is this
Yes, sir.
value?
Resistive.
Resistance, right? So if this is F1, for example, and this is F2, right? So what is this value?
Root 2R, sir.
Yeah, good. No? What is that R root 2R? Understood?
Sir.
Understood, right? So now tell me,
Yes, sir.
at F1, right, at FR, the circuit is resistive, right? No confusion. At F1, is the circuit is inductive or capacitive? At F1,
Inductive, sir.
Inductive.
inductive, right? So how the impedance triangle will be at that time? So it will be something like this, right? If this is Z, right? So this will be R here. So this will be omega L minus omega C, right? Agree?
Yes, yes.
Yes, sir.
At F1. Similarly, at F2, the circuit will be capacitive, right?
Capacitive.
And it will be something like this. So here it will be negative, and here this will be. So this is omega, sorry, 1 by, what is this? 1 by omega C minus omega L. So this is R and this is Z. So this value is equal to R and this value is equal to R. So that's why so Z is root 2 R here and this is also root 2 R. So these are the impedance triangles, right? This is for at F1 and this is for F2. Understood? So you have any questions here? Just simple.
No, sir.
Okay. So now, so we'll talk about the lower off-power frequency F1, right? So at F1, so this XL is more when compared to XC, right? So that means we can write the equation something like this, 2 pi F1C, right? Okay. No. At lower, the circuit will be inductive, right?
Sir.
No,
2
I
pi
think.
F.
So frequency less than resonant frequency, the circuit will be capacitive.
So this is the one, right? No. F1 is corresponding to capacitor, right?
Yes, sir.
So this is F1 and this is F2. In previous class, we discussed this. So we are discussing this, right? You remember this. So this is from 0 to this point, the circuit is capacitive. From 0 to resonant frequency, the circuit is capacitive. From resonant frequency to onwards, the circuit is inductive, right? Okay.
Yes.
So from F1 is in inductive region or capacitive region?
Inductive.
F1,
Capacitive region.
capacitive, this
Capacitive
is
region.
capacitive. So here this 1 by omega C is more when compared to omega L, right? So here F2, so that will be inductive. Change this. So here omega L is more when compared to that. So now at frequency, so this is 1 by omega C minus 2 pi F1 L. So this value is equal to R, right? Agree?
Yes, sir.
Yes, sir.
Okay. So now this is it will come to a quadratic equation. It will be 4 pi, just correct me if I'm wrong. 4 pi ELC into F1 square, right? Plus 2 pi RC into F1, okay? Minus 1, I think, equal to 0. Is this correct?
4 pi square, sir.
Sir, 4 pi square.
4 pi, oh yeah, 4 pi square. This is correct?
Yes, sir.
Okay. So what are the roots for this one? So we have two roots, right? F1, what is the F1 here? What is the roots for this? To simplify the roots. So what is the first thing is minus B, right? Minus B plus or minus
Yes,
B
sir.
square minus 4AC by
By 2A.
So if the
2A.
2A is 2 into 4 pi square LC, right? And minus B. The first term is minus B by 2A. So what is minus B by 2A? So is it minus R? So here this 4 pi L, right? Plus or minus.
Yes, sir.
The first term is
2.
R square, I think. Plus 4 L by C. Just check it once. Check this once.
Correct, sir.
Yeah.
Yes, sir.
So how many roots it have? Two roots, right? One is minus r plus r square 4l by c, and another one is minus r square. So which is the valid root? So if you notice that, so one of the root is negative, right? Okay. So one of the root is negative. So don't take that negative one. So negative is negative frequency. There is no meaning, right? So you have left with only one frequency. So minus r plus, no, plus or minus r square plus 4l by c by 4 pi l. So this is positive or negative? It is r square plus 4l by c. So obviously, so this value is greater than r only, right? Because we have this additional term 4l by r. So this value is always greater than 0 only. Okay. Understood?
Yes, sir.
Okay. So you have one frequency. This is the f1 is minus r plus r square by 4l by c by 4fl. So this is the formula for lower power frequency f1. Similarly for f2, so f2 you have what is the equation? 2 pi f2l minus 2 pi f2c, so which is equal to r. So if you solve this one, right? So what is f2 value? Tell me. Solve this quadratic equation and tell me the f2 value.
Sir, r plus square root of r square plus 4l by c
R
by
plus,
4
wait, R plus
square
Square
root
root of r square
r
plus
square plus
R
4l
square
by
plus
c
4L by C
by
by
4 pi l.
4
4
pi
pi
l.
L. Good. So again you have plus or minus, right? You have also plus or minus here. So why we are not considering that minus value?
Negative value.
Negative value, sir.
It is, it's negative value, right?
Yes, sir.
So this is for F2 value. So what is bandwidth? F2 minus F1. What is F2 minus F1?
R by 2
R by 2 pi L.
pi l.
R by
2 pi l.
2 pi L. R by 2 pi L. So this can be written as 1 by 2 pi, right? L by R, 1 by 2 pi L by R. Okay. So if you multiply with FR here, so FR, okay, into 2 pi FR, right, L by R. One second. So what is this? FR. So this is 2 pi FR is omega R, right? Into L here, into R here. So what is this entire thing?
1 by Q.
1 by
Q,
QR.
sir.
That is
1 by
FR
By
by
Q, sir.
QR, right? Agree?
QR. Yes. Yes, sir.
Yes, sir.
So that means you have different formulas for bandwidth. So F2 minus F1, so which is equal to resonant frequency FR by QR. So in other words, QR can be written as, how to QR? So it is F2 minus F1 by FR. Check this one. No. I think it is an opposite one, right? QR. So this is, if you equate this, QR is FR by F2 minus F1. So you have any questions?
No, sir.
Okay, right. So we'll stop here. In next class we will discuss. I will try to solve some problems on this.